This is a lecture for Math 107, Chapter 5, and it is on inverse matrices and determinants of matrices. The inverse of a matrix, first you only have inverses of square matrices. So if you have another matrix and you multiply these two matrices together and you get the identity matrix, then those are called inverses of each other. This is on the test. If I have two matrices A and B, and I multiply A times B, and I get the identity matrix, then A and B are inverses. All right. There's a notation for the inverse, and it's similar to the notation for the inverse of a function. You put a little -1 here, and that means it's an inverse of the matrix A. That's the inverse of matrix A. In this case, you could say B was A inverse. You could also say A was B inverse, because it goes, what's the inverse of 1? It works the other direction too. Okay, this is matrix A. And you can multiply these in any order. These are square matrices. Remember, they're always square matrices, so you can multiply them in any order. And when you do multiply them in either order, you get the identity matrix I. Remember, the identity matrix is a matrix. It's a diagonal matrix with only ones down the diagonal, zeros elsewhere. And here's an example. Let me clear this board a little bit. I'm going to take this matrix, 2 by 2, 2 minus 7 minus 1 and 4, and I'm going to multiply this matrix, 4, 7, 1 and 2. Now carrying out the matrix multiplication, 2 times 4 minus 7 times 1 gives me 8 minus 7 is 1. Alright, so that was the first row against the first column. Now first row against the second column gave me a 0. I'm going to the second row and going against the first column. So I have minus 1 times 4 plus 4 times 1, that's a 0. And then I take that second row, I go against the second column, and end up with minus 7 plus 8, which is 1. This is the identity matrix. These two matrices are inverses of each other. Note this notation problem. We've had this before with functions. F to the minus 1 does not mean 1 over f. It means the inverse function of f. And the only way to determine if they're inverses is to compose them. You have to use composition. Right. And these are functions of x. So you have f inverse, it's a function, say, of x, composed with f of x, and the answer is just plain old x. You get the x back. That's what it means for functions. But this minus 1 as a superscript right on the f does not mean 1 over f like it does in every other case. Instead, it means the inverse of the function f. For matrices, we use the same idea. A with minus 1 does not equal 1 over a. Instead, it means the inverse of the matrix A. But the operation associated with inverse in matrices is matrix multiplication. So here it was composition for functions, here it's matrix multiplication. The existence of the inverse matrix, the fact that it even exists, is tied to what's called the determinant of the matrix. So we have two kind of vocabulary words here. One is the inverse matrix, which we just talked about, and the other is the determinant. So I'll show you where this comes about from using a small matrix, a 2 by 2 matrix. Now if I have any 2 by 2 matrix, and I'm just going to call the elements instead of doing this, what we usually do, A11, A12, and this would be A21 and A22. Okay. Instead of writing it like that, I'll write A, B, C, D. It's going to be easier to handle, so I'm just going to do it like that, A, B, C, D. Now I'm going to tell you that the inverse is 1 over AD minus BC times this particular matrix. So this is a scalar multiplying a matrix. but I'm going to write it in this form with the scalar out in front. All right, the scalar has in the denominator a times d, which is these numbers, minus b times c, which are those two numbers. This can't be 0 because you can't divide by 0. If it's 0, then the inverse doesn't exist. If it's not 0, then the inverse exists. This is the determinant of the matrix. Now we have special notation for the determinant of a matrix. We can write DET, meaning the determinant of matrix A. You can write determinant right in front of the matrix, and here's how you take a determinant. This is for a 2 by 2, and everything will reduce to a 2 by 2. You multiply the terms starting in this corner. I guess that's the upper left-hand corner. So you go A11 times A22. Then you go in the other direction, multiplying the terms. You make an X there. That's A21 times A12, and you subtract them. If you're using the ABCD notation, you'd multiply A times D. That's, oops, I got a blue. That's going in this direction. And then you go in the other direction, C times D, and you subtract them. So it's AD minus CB, or BC. I usually think of the pattern as going down and then going back up in that direction. And that is called the determinant. You can write this little DET out in front. You can also write the matrix inside of what looks like absolute value signs. That's equivalent to saying determinant. And again, if that determinant is 0, then the inverse for this matrix A does not exist. And here's that statement in big bold letters. Of course, this is on the test as well. If you take the determinant of a matrix and it's 0, then the matrix does not have an inverse. If you take the determinant of the matrix and that value is not 0, it could be negative, it can be positive, it can be a fraction, doesn't matter. As long as it's not 0, then the matrix has an inverse. So here are some examples. Let's take the determinant of the matrix 4, 7, 1, 2. Well, that will be 4 times 2, going in this direction, minus 1 times 7. That's written out here. The answer is 1. This matrix has an inverse. Now look at the second matrix here. 3, 12, 1, 4. 3 times 4 is 12, minus 1 times 12, which is also 12. This is 0. This matrix has no inverse. Having an inverse is tied to whether the equations are linearly dependent or independent. Remember that when you solve a system of equations, sometimes there was no solution. For example, if I had say this was one equation, and you know if you have a solution, then the other equation would intersect that line, and that point of intersection would be the solution. But if these are parallel, they never intersect, so there's no solution. Look at these. Let me clear the board here. Look at these values right here. The first line is 312. The second one is 1, 4. If I multiplied the second line by 3, the second row by 3, I would get the first row. These are basically the same, just multiples of each other. Okay, so it's sort of tied to that. I'm not going to go into that right now. I just wanted to point it out. So now look at the third example here, and in this case I used what look like absolute value signs or magnitude signs to take the determinant. This means take the determinant. That would be minus 6 times 1, and subtracting minus 1 times minus 4, and I get a negative 10. It has an inverse. I want to point this out, that even if that number is negative, it will still have an inverse as long as it's not 0. Now I would just like to show you that what I said was the inverse of a 2 by 2 matrix is indeed the inverse. So here I have this matrix ABCD, and I said that the inverse was 1 over the determinant times D times minus B minus C times A, and A for the matrix. If they're inverses, then when I multiply them together, matrix multiply them together, I had better get the identity matrix. So I'm just going to multiply them together, and the scalar can sit out front until the end, and I'm taking D minus B and going against the first column. And when I do that, I get AD minus BC. When I go against the second column, I get DB minus dB, which is 0. Now I move to the next row, and I take minus CA times the first column, and I have minus C times A plus A times C. That gives me a 0. Then I move to the second column, and I get AD minus BC. And scalar multiplication, remember, that will distribute to every term. Won't matter here or here, but it sure will make a difference here, and the result will be 1, 0, 0, 1, which is the identity matrix, showing that this is the inverse of this. Notice how this was constructed. Here's the determinant, 1 over the determinant, so the determinant's sitting right here, the inverse is here. Then the A and the D are switched. So the A is here, goes down, these diagonal terms just get moved around. The D comes back up here. Now, on the off-diagonal terms, they just change sign. The B becomes minus B. The C becomes minus C. So if I have a matrix like this, 3, 5, 1, and say 9, and that's my matrix A, I can easily compute its inverse. It's going to be 1 over the determinant. The determinant will be 27 minus 6. Remember, I multiply the 3 times 9, subtracting the other multiplication. And then for the matrix, that's a scalar. For the matrix itself, I will have to switch the order on the diagonal, so I get a 9 here and a 3 here. The off-diagonal terms just change sign. And now I've constructed the inverse. The only inverses you'll have to construct for the class are 2 by 2 matrix inverses as shown here. Just by using this formula of ABCDs, just substitute that in. First check that the determinant isn't 0, and then go ahead and just plug into this equation. Use that as a template. And here's an example. Here's my 2 by 2 matrix, 6 minus 4 minus 1 and 1. First check the determinant to see if it's 0, in which case you can stop and say there is no inverse. Taking the determinant, I get 6 times 1 minus negative 4 times negative 1 times negative 4, which gives me 2. Okay, so the determinant, the inverse exists. Now what is the inverse? Okay, it's 1 over the determinant. So it's going to be 1 over 2. You see that right here. Then the terms on the diagonal, the 6 and the 1 change places, so the 1 goes up here and the 6 comes down here. The off-diagonal terms change sign. Minus 4 becomes positive 4, minus 1 becomes plus 1. And now we'll verify it. We multiply them together, so here's that scalar sitting out in front. I'll leave it out there till the end, and I have this matrix multiplying my original matrix, and I end up, if I still have the scalar out in front, with a diagonal matrix with 2's on the diagonals, but I'm dividing by 2, so I end up with the identity matrix. And now I'll show you how to take the determinant of a bigger matrix. So here's a 3 by 3, and there's a homework problem on it, and there might be one on the test. I can't remember what I put on the test. Okay, so here's your 3 by 3 matrix. Right. Here's how you do it. You expand along a row or column. And I'm going to expand along row 1. So I take the 1, and the 1's going to go here. The second entry is going to go here with a sign change, and the third is going to come over here, and that's going to make my third. I'm expanding along row 1. The rule is that you add I and J, and if they're even, you don't change sign. If they're odd, you do. This rule allows you to expand along any row. For example, if you have one with a lot of zeros, you definitely want to do that. But in this case, I'm just going to say expand along row 1. That's all you should do for this class. Now, when you have found this one entry, you then look at what's called a cofactor matrix. You mentally, let me see if I can do this with it. You mentally cross off the row and column where the 1 is sitting, and you look at the matrix that's left over, 5, 6, 8, and 9. That's a little 2 by 2 matrix, and you take the determinant of that. So it's 1 times the determinant of what's called this cofactor matrix 5, 6, 8, 9. Okay, let's move to the next one. I'll have to clear the screen and show you that one. So in this case, I'm talking about the 2. It changed sign, but I mentally cross off the 2, the row in the column where the 2 is sitting, and I'm left with 4, 6, 7, 9, and that 4, 6, 7, 9 appear right here. I do the same with the 3. I cross off the row and column where the 3 is, and I'm left with 4, 5, 7, 8, 4, 5, 7, 8, and that matrix is right there. Now I take the determinant of those 2 by 2's because I know how to do that, and I do it in the standard way. So it's 1 times the determinant of that matrix minus 2, determinant of this 2 by 2, and 3 times the determinant of this third matrix. The determinant of the first matrix would be 45 minus 48. The determinant of the next matrix is 36 minus 42, and the third one is 32 minus 35. When I work all that out, I end up with a 0. That says the original matrix has no inverse. In fact, these equations are somehow scalar multiples of each other. You can't see it as you could with the 2 by 2. Once you get a lot of terms, you can't tell just by looking at a matrix that the equations aren't all linearly independent. But when you take the determinant, you find that out. So again, just to summarize, to take the determinant of a 3 by 3 matrix, you expand along the first row. That means you take the entries in the first row, and that gives you, they become multipliers of smaller matrices. You leave the signs alone for the first and third one. You change the sign for the second one. If this was minus 2, you'd write plus 2. Okay. Then you mentally cross off the row and column. For example, where the 1 is, this becomes a matrix. It's a 2 by 2. You can take its determinant and multiply by the 1.